Hello there, and welcome to Grade 10 Chemistry. In this lesson, we're going to review the basics of the composition of atoms and how that's related to the periodic table of elements. So atoms are the building blocks of the simplest form of matter, which are the elements. And the elements are what go together to make all the different forms of matter that we have in our universe. And so we're going to look at the relationship between the arrangement of the elements on the periodic table and how that goes with the arrangement of all the different particles in the atoms. So let's get started. So just as review, hopefully you recall that there are two basic regions of an atom. You got the central region called the nucleus, where you're going to find the protons and the neutrons. Your protons have a positive charge, right? And your neutrons have a neutral charge or no charge, 0. And then the other region is the area where the electrons hang out, which are these shells, and they have a negative charge, and they exist in these layers that are quite a good distance from the nucleus. And the quantity of these particles is what makes the difference between one atom and another. The main mass, electrons don't have very much mass. The mass of an atom comes from the nucleus here, and so it's the protons and the neutrons that have most of the mass in an atom. So the periodic table has some clues as to the makeup of all the elements that are on it. And so you can tell the number of protons and the number of neutrons in an atom from the values that you see on the periodic table. So you see these atomic numbers here, and that's going to be the number of protons on this periodic table. They're all blue, and all the elements are arranged in order from left to right, top to bottom, in order of the number of protons. The atomic number, same as the number of protons. The other part is the mass number, and you can see it's often a decimal value, and it's down at the bottom here, it's in red. And that is the total number of protons and neutrons in the nucleus of an atom. And the reason why it's a decimal is because it's measured using a device called a mass spectrometer, and there's more than one number of protons for many of the atoms that we have. And so what you see there is an average number of protons and neutrons. And so what you have here then is this weighted average that we'll just round it off, and we'll come up with the most common number of neutrons just by subtraction. So for our example here is sodium, good old sodium here. We see there's an 11 there, and so that means 11 protons in the nucleus. And then we've got 22.98 blah, blah, blah. That's roughly 23. So 23 minus 11, that's going to give us 12 neutrons. So you just need to subtract, and you will end up with the number of neutrons. So that's how you figure out your nucleus. So the next part of the atom that we need to work out is the electrons, the number of electrons that the atom has. And the Bohr-Rutherford diagram works well for that. So the nucleus we already figured out. For sodium we got 11 protons and 12 neutrons. And so we want to add some electrons around that. So a nice rule of thumb for the first 20 elements is to follow 2882. Of course, if we go beyond that, there's a more complicated pattern that the electrons follow, but we'll get to that in later courses. So for now, 2882 works just fine. And what you can do is take the same number of electrons as protons for a neutral atom. So if it's neutral, the protons equal the electrons. So in this case, we're going to need 11 electrons. We'll start at the first layer, and we'll put 2 electrons there. So yay, we've done our first layer. So now this one's full. We'll go to the second layer. We can go up to 8. So 8 and 2 makes 10. We're almost there. 1, 2, 3, 4, 5, 6, 7, 8. Right? Plus the 2 in the inner layer, we're at 10 electrons. And so that outer layer only has 1 more to make 11. Put it up here. And there you go. Nice Bohr-Rutherford diagram. All right, so another nice way in which the periodic table is arranged is in groups and periods. So groups are the vertical columns. So this would be group number 1. You can see it's labeled 1, 2, 3, and each one of these is a group. And then the periods is the horizontal rows. So hydrogen and helium are in the first period, and then lithium across to neon is in the second, and they're numbered down the side here, 1, 2, 3. And so you can use it just like you would in a game of Battleship and find the elements by their coordinates from their group or their period. And a lot of the properties of elements that we'll look at later on are related to where you might find them on the periodic table. So if we start at group 15 and number 3, group 15 is here. Period 1, 2, 3 is going to be phosphorus. So we put the P for phosphorus. Then group 17 is here. And period number 5 is here. So that is iodine. And then we'll go group number 2. And period number 7 all the way down here is number 7. So that's radium. All right. And then we will go to group 16, which is way over here, and period number 5, which is here, and it's tellurium. And look at that, spelled the name, pirate. Another neat feature of the groups and the periods is it can tell you the basic structure of an atom. The periods tell you how many layers an element has. And so anything in the first period is just going to have 1 layer of electrons, second period 2 layers, and 3, 4, 5, up to 7. You can tell right away how many layers of electrons there are. The other feature is with the groups, and the groups are related to the number of valence electrons, at least for these 2 columns here. And if you skip the middle and do these other columns over here, the group number corresponds to how many valence electrons they have. And so the ones that we're going to use are going to be just in these 2 sections. And you can basically tell how many valence electrons there are by the group number. Now you're going to skip this middle section because things are a little more complicated in there. And when you get over here to boron, just call that group number 3 for purposes of coming up with valence electrons. So 3, 4, 5, 6, 7, 8. And of course helium is an exception. It's full with 2, so it really belongs over here for this purpose. So you can tell right away how many layers of electrons and how many valence electrons there are. And if you remember, to show that is with a Lewis symbol, and that's just the symbol of the element with the number of valence electrons as dots. So if we start with phosphorus, which is over here, we can see it's in group number 5, and we'll give it 5 dots. So I'll put phosphorus down here, 1, 2, 3. Remember, do like your compass points first, and then double up after that. So it's got 5 valence electrons, and you arrange them like so. Calcium, which is this guy over here, you can see it's in group number 2. It's only going to have 2 dots. So that's a quick way you can tell how many valence electrons your atom has. Now the elements themselves, when they put together that periodic table, the reason why they arranged them the way they did is because of the physical and chemical properties that the elements showed. And some different types of elements showed up right away. A lot of elements, the majority of the elements in the periodic table are metals. And so we got good old copper here as an example. And so copper is, of course, shiny. Malleable means you can mold it into different shapes. Ductile means that you can stretch it into wires. And of course, because it's a metal, it conducts electricity. So those are some common properties of metals. And a big section of the periodic table is metallic elements. On the other side, we have a whole bunch of non-metal elements. And these are pretty much the opposite. They're not so shiny. They're more brittle. They don't conduct electricity, and a good example here is sulfur. You can see it's this yellow, crumbly, almost like a powdery substance. Like you make a powder out of it, or like a crystalline substance. In between, we have these guys called metalloids, which have some properties of both. So this is a lump of silicon right here, and you can see it's shiny like a metal, but it's also brittle. If you hit it with a hammer, it'll shatter just like the sulfur. And so it'll have a mix of properties of the two, and the interesting thing is that you'll find it in a distinct area of the periodic table, which we'll look at next. So the periodic table was arranged based on properties, and so surprise, surprise, the metals all ended up in a particular section. And so it's pretty much everything on the left side of the periodic table, with the exception of hydrogen. Hydrogen doesn't have any metallic properties. It's a non-metal. And then on the other side here, we have our non-metals. And so it forms by all of these guys. So these are metals, and these are non-metals. And so you can see this, this gray staircase in between. Those are metalloids. And so it's pretty neat that these elements with similar properties end up in particular sections of the periodic table. And the periodic table is arranged by atomic number, which is protons, and you can see how that pattern starts to emerge. It's pretty cool. So some groups on the periodic table have been given names because they are a common way of distinguishing different types of elements based on their properties and based on their location on the periodic table. So the first group here, group 1, are called alkali metals, and these are the most reactive metals on the periodic table. The next section over, they're called alkaline earth metals, also very reactive, not quite as much as group 1, but for similar reasons, which we'll get to. On the non-metal side, group 17 and 18 are the most common. Group 17 are called halogens. They are these 4 or 5, I'm not sure if astatine qualifies. And the last group are the noble gases, also very important, and that's the last column on our periodic table. Very non-reactive, so notable compared to all the rest, which are quite reactive. So 2 last sections we're going to just note before we go here. The first is the transition metals. Transition metals are between groups 3 and group 12, and you can see a lot of common metals in there that you've probably heard of before, things like zinc and copper and silver and gold and mercury and nickel and iron, and of course some others that you might not be as familiar with. And so those, that's another section that you might hear referred to. And the last bit here are the lanthanides and actinides, and they're named after the first 2 elements in those rows. And they actually belong in this section of the periodic table, but it'd be kind of long and skinny if they actually inputted it in there. And so, so they have removed that section and put it below. Probably the most common element in there that you've probably heard of is uranium. There's also plutonium in there and a few others that are less common. But it's nice to have an understanding of what people are talking about when they say lanthanide or actinide. It's that section of the periodic table. Okay, hope that helps. We're off to the races here, and we'll see you soon.